Pressure has a lot to do with our weather. So the atmosphere exerts a pressure. It's called atmospheric pressure. Variations in that pressure cause wind and other changes in the weather. And by looking at where the atmospheric pressure is high and low, meteorologists can gain information about what's going to happen with the weather. So here's a map showing a low pressure region over here. Low pressure is usually associated with unstable weather. So you might have rain or storms or something. Over here, a high pressure system, usually that indicates clear weather. So like this barometer, we have this little weather station here in the lab, and it's got these little pictures. Now this is showing, looks like raining going to just a cloud. So that tells us, it's telling us that based on what the barometric pressure is doing. Barometric pressure has been coming up, and so that's predicting that the weather will become more stable, which around here doesn't really even matter. Not so much. What's it going to be like today? It's going to be sunny and warm, possibly hot. Yeah, so boring. Okay. The number of gas particles in a volume decreases as you go higher into the atmosphere. So higher altitude, the gas pressure is less, the atmospheric pressure is less because there are fewer particles. The air gets thin. It literally gets thin. Here we have, these look like two mason jars, don't they? Two mason jars, and they each have a pink gas in them. So here you have fewer gas particles, and here you have more gas particles. We could assume they're at the same temperature, so they're moving around at the same speed. There's going to be more pressure in this one because there are more particles, and so they're going to collide with the walls more frequently and cause more pressure. Fewer gas particles would mean a lower pressure. So pressure also explains a phenomenon that happens when your ears pop. So if you fly in an airplane, this may happen, or if you go up into the mountains, this may happen. As you're going up in altitude, the pressure on the outside of your eardrum becomes reduced because higher in altitude, the pressure is lower. Your eardrum separates the outside from the inside of your ear. The inner ear also has air in it. And when the pressure change happens, this normal pressure in here will cause your eardrum to bulge outwards. Normally, that's just mildly uncomfortable. If you have an ear infection, that can be excruciating. And this is the reason why small children scream and cry on airplanes. Their ears hurt. It's not because they're out to get you, their ears hurt. So what happens? Does your eardrum burst? No, you have a eustachian tube that will allow the pressure to equalize, and that's why yawning or chewing gum or something helps to get that open. If you've got a cold and you're all congested, that might be swollen up and it's not going to pop very well, and then you're just going to have a lot of pressure in your ears.
How do you know the baby?
Well, for a baby, you want to give them something to suck on or something to drink. Yeah, just to get that moving. And it's a bigger problem with young children because their eustachian tubes are smaller. And so it's harder for them to equalize. When you come down and the outside pressure is getting larger and the inside pressure is less, then your eardrum's going to bulge the other way. And it's going to do that until you can get the air to go back in. How do we measure the pressure of the atmosphere? Well, we use a barometer. This is the original type of barometer, a Mercury Barometer. Here we've got a dish of mercury. Mercury is a metal, but it's a liquid at room temperature. It's also very dense. Here's a glass tube. You take a full glass tube of mercury, you invert it into the dish, and a little bit of it will come out, provided this is long enough. The atmosphere will support a column of that's 760 millimeters in height. That's equal to 29.92 inches. So that's a significant column of mercury. Why does the mercury stay up there? It's because there's a balance between gravity pulling down on the column and atmospheric pressure pushing down here. Pushing down on this surface is pushing mercury up into there. And so there's a balance between gravity and the atmospheric pressure. If the atmospheric pressure is less, if like Torricelli, you take this thing and you walk up the mountain with it, as the atmospheric pressure decreases, the column of mercury gets shorter and shorter. And as you come back down and the atmospheric pressure increases, the column of mercury gets higher. Doesn't matter the diameter of the tube or anything, it's always the same height. So a millimeter of mercury is like the original unit of pressure. It's a length of an element, so that's weird, but it comes from this barometer. This is very low tech. A glass dish, a glass tube, some mercury, and then you need a ruler. And you can measure atmospheric pressure. One torr is a different name for millimeter of mercury. Same thing. Torr in honor of Torricelli, the guy who originally did this work. So a millimeter of mercury is a torr. Average atmospheric pressure at sea level is 760 millimeters of mercury. So we call that 1 atmosphere. So here's some units of pressure. Here's an atmosphere, abbreviated ATM. We can measure it in inches of mercury. That often looks like in mercury, so that can be confusing. This is 29.92 inches of mercury. A torr, which is 1 millimeter of mercury, so 760 torr exactly is 1 atmosphere. All of these things here in this column are equal to each other. So 1 atmosphere equals 29.92 inches of mercury equals 760 torr equals 14.7 psi. So psi stands for pounds per square inch, force per unit area. And it is psi, it's not psi. A pascal is the SI unit, a newton per square meter. Those are the base units of force and area. And that's abbreviated with a PA. So 101,325 pascals is equal to 1 atmosphere. Why do we have so many units? Because they are useful in different situations. The ones that are important to us in chemistry are atmospheres and torrs, or millimeter of mercury. We use those a lot. So we should be able to convert between pressure units. You can do pressure unit conversions always in one step, because the way the tables are set up is they're showing you all the different things that are equal to each other. So this first line you should memorize. An atmosphere is 760 torr, which is 760 millimeters of mercury. That is an exact relationship. It's been defined that way. Infinite sig figs. So if you're converting between torr and atmospheres, that 760 doesn't come into counting sig figs. You just ignore it. It's not going to limit anything. So you should learn this top row because we're going to use that a lot and it'll save you a lot of time. The bottom row here, you might need to refer to it, but if you needed those on an exam, I'd give them to you. Okay, I don't expect you to remember all of those. So this would allow us to convert directly from pascals to inches of mercury, or from PSI to torr. These are all equal to each other, so you don't have to go through multiple steps. So the local weather report announces the barometric pressure is 30.44 inches of mercury. Convert this pressure to PSI. So dimensional analysis. So what am I starting with? I'm starting with 30.44 inches of mercury. I just do one conversion factor. What unit am I going to? I'm going to PSI. The unit I'm coming from is inches of mercury. units cancel out. Then I go to the table. And this is really the only ones you're going to need. There are probably some other weird ones on the, I think those are on the green chart. But these are really the only ones you need. So PSI, 14.7. Inches of mercury, 29.92. Done. 30.44 times 14.7 divided by 29.92. My calculator is saying 14.955 PSI. Oops, I dotted the S. There we go. What about sig figs? Our starting number had 4. 29.92, that's not exact. 4. 14.7, also not exact. I really wish you would have put it's really 14.69. And it can be measured out even more precisely. This only has 3 sig figs. So that's going to limit our answer to 3. Keep the first 3, and that's going to round up to 15.0 PSI. Any questions? Yes? Do we have what? Oh, negative pressure. No. You can't have negative pressure. No. If you talk about negative and positive pressure, it's just a pressure difference. So you can have a, and this is how they would keep a clean room. For certain types of engineering, they need to have a clean room, and in medicine too. So you don't want anything coming in the air or anything. And so to maintain that very, very clean room, they keep a positive pressure in the room so that there's always air flowing out of the room and never air flowing in. So that's called a positive pressure. You could have negative pressure if you had something in there that you didn't want to get out, but that's not really a negative pressure. It's just that the pressure inside the room is lower than outside, and so the pressure is always pulling air in instead of out. But you can't have negative pressure.
So when you're measuring vacuum on a pressure gauge, they'll say, I have 0, and then they'll say inches of mercury.
Mm-hmm.
They got to 30 or something like that. So it's.
I mean, you can't get below a perfect vacuum.
So perfect vacuum is.
That would be the absolute.
14.7.
That would be the absolute 0. And this 14 psi. So when you pump up a car tire or a bike tire, and it says, pump it up to 55 psi. It's actually in relation to the external pressure. So a lot of times things are measured relative to the atmospheric pressure, not actually relative to 0. Yeah. How do you measure pressure in a container? Well, of course, we have lots of fancy pressure gauges now, but this is the original kind. And it's similar to the barometer. It's called a manometer. Here we're making use of liquid mercury again. So there's a U-shaped tube here that connects the gas under pressure to the atmosphere. So imagine this tube here. If this was open at this end, what would the mercury do? What would water do? It would go to the bottom, right? And these levels would be equal, right? Why is this side lower? Because this gas is pushing down harder than the atmosphere is pushing down on the other side. So we can measure the difference in pressure between the atmospheric pressure and what's inside this container by measuring with a ruler the difference in those columns of mercury. And that would be in millimeters of mercury. You can convert that to whatever unit you want. If the pressure inside is less than the pressure outside, then this side will be lower and this side will be higher, because then the atmosphere is pushing harder than what's inside. So that measures the difference between atmospheric pressure and what's inside the container. Any questions?